a very short amount of time. Any particle, including the Higgs, can do that. This is how we began to search for the top quark before we had accelerators that were energetic enough to actually make one in the laboratory. It's called precision physics. You make a very, very accurate measurement of something. You make a very, very accurate standard model calculation, and there's only one unknown, the mass of the Higgs, and so you can compare the two and try to deduce the mass of the Higgs. We've been trying this for 30 years now, ever since the Higgs mechanism was proposed, and we're beginning to hone in, but unfortunately the Higgs effects on other processes tend to be rather wimpy compared to, say, even the small effects of a top quark. Very, very subtle effects. So it's hard to exactly pin down. The top quark, we had predicted its mass to within 10% before we actually found one. The Higgs, right now, I think we're talking about a mass somewhere between 100 times a proton mass and 200 times a proton mass. So that's the best guess today from this precision data. And we continue to collect precision data, and so presumably those limits are going to get narrower and narrower. But why not just make one? Between 100 and 200 proton masses, so that's how much energy you have to put into a small region of space. We ought to be able to do that. At Fermilab, we have a TeV, that's 1 trillion electron volts. It's plenty enough energy, in principle, to create a Higgs. The problem is, you pour all this energy into a small region of space, and what happens? Well, most of the time, you get protons and antiprotons, or electrons and anti-electrons, or pions and kaons, and all of the zoo of particles, even top quarks and anti-top quarks. Everything you can produce, you will produce. Right? That's sort of the way quantum mechanics works. Everything is probabilistic. The more probable an event is, the more you will see coming out in your detector. And we worked out the probability of creating a Higgs particle in the standard model. There's one unknown, which is its mass, so you just sort of take a guess, supposing it's 200 times the mass of the proton, what would the probability be? And the answer is very small. So we're going to Fermilab and looking for these things, but the probability is so small that, in fact, it's so far not even expected that we would have seen even one such event compared to the millions upon millions of other quantum particle production events. So you're looking, this is truly looking for the needle in the haystack. If we make one, it'll be pretty clear. The signature of a Higgs particle in a bubble chamber, or a modern version of a bubble chamber, is going to be quite distinctive. So we believe that once we make them, we'll know, but we just haven't made one yet. The American strategy at Fermilab has been to upgrade the intensity of the beam. It's very difficult for us to increase the energy. We've already done the upgrade to 1 trillion electron volts. It was a big, expensive project. And upping it even more would require stronger magnets, bigger accelerator, and we just don't have the funding at the moment for that kind of a project. So we're just trying to make more and more and more protons and antiprotons collide together. If you have a low probability event, it's like, rolling the dice, or more appropriately, buying lottery tickets. And if you've only got a 1 in a million chance, that's all you got. You might as well buy more and more and more and more tickets. Actually, that's a very bad strategy with the lottery, because you have to pay money for each of those tickets. But with the Higgs, that's really the idea at Fermilab. Increase the luminosity or intensity and hope that we get enough events that 1 or 2 of them will be a Higgs. The Europeans decided to take the brute force approach. There's this accelerator there called CERN, the European Center for Nuclear Research, and they have just recently shut it down, and they're revamping the energy and the magnets and the whole system so that they're going to go up to much higher energy. I believe their new energy around 2007, if all goes well, will be 17 trillion electron volts compared to our 1. So they're going to go for high energies, which also increases, it turns out, the probability of producing the Higgs. And they will certainly be able to see them if they're there. If they're there where we're expecting them right now, in 2007, the Europeans should be able to find them. It turns out that the United States made a big effort to find the Higgs a long time ago. In the 1980s, a bunch of physicists got together. Right? This standard model was in existence. We knew almost all the pieces that we know today, except for the Higgs. And so in the early 80s, it was proposed that we build a truly gigantic accelerator. It was going to be called the Superconducting Super Collider. It's a little ridiculous. There's a lot of supers. Physicists need some new adjectives, I think. Superconducting because if you really want ultra-high energy protons to go in a circle and not fly away, you've got to have a big old magnet to make them curve around in a circle. This machine was mammoth proportions. It was going to be something like, 53 miles around. 53 mile around this ring. And the magnets, if you just use a conventional magnet, it's not strong enough. If you use a very powerful electromagnet, it's not strong enough. You need superconducting metal, which can withstand enormously high electric currents to create the magnet. So that's why it was superconducting. And super collider, because it was going to be extraordinarily high energy. We're talking 20 TeV in each particle beam that was going to smash into each other. So 40 trillion volt collisions, electron volt collisions. And that would have been plenty. And had this gone as was planned at the time, it would in fact already be running today. In fact, by the late 1990s, this machine would have turned on. It was proposed in the 80s. It went through a lot of reviews, and then first in the physics community and then in the United States political community. Congress approved the project. It was funded. The original estimates were $8 billion. This is big science, the biggest particle physics experiment since the Manhattan Project, which really doesn't belong in the field of particle physics research. That was a U.S. military project. That $8 billion figure started climbing, and they started building the tunnels. They started designing and building the magnets. Everything was going, and every year, of course, Congress would revisit. There were more debates. And finally, in the early 90s, times were tougher, and the project was canned. It was pretty much, I think, a political decision, not a science. In fact, it was completely a political decision, not a scientific decision. They had already spent, by that time, $2 billion digging part of the tunnel, designing some of the system. There's many tragic aspects of this superconducting collider's demise. You know, it's very sad, in a certain sense, for the physics community that we lost this opportunity to find new particle of nature. But, you know, it's also tragic when the U.S. government essentially threw away $2 billion. I mean, you can argue about whether it's worth the money to design such a facility. It's an interesting and important argument, and physicists were also arguing this just as much as the politicians were. But nobody wants to just start a project and then throw it away. So I think there were many lessons learned, and one of them is if you're going to do a project like this, we really are going to have to make it an international collaboration. We're going to have to make sure that the funding gets spread out in some way, that it's not going to just disappear in the middle. Just to set the stage, I guess it's worth looking at the financial scale of some other big science projects. We have a space station in orbit right now, and that project, I mean, it's hard to estimate costs of these things, but it's roughly a $25 billion project. And I think most scientists, even astronomers, physicists, agree that the science coming out of the space station is probably less obvious and less exciting than the physics that was aimed for in the superconducting supercollider. The motivations for the space station are somewhat different, I think. The Human Genome Project is a biology experiment, and that was $3 billion, so somewhat cheaper than the superconducting supercollider, and that one was a great success. And so it's interesting to sort of, first of all, compare these projects. Another useful number to look at is what fraction of the U.S. federal budget would the superconducting supercollider have been? And the answer is 1/100th of 1% of the U.S. federal budget. So on the one hand, it's a huge amount of money. On the other hand, it's small compared to all the other monies that we're spending. And, you can imagine the political and social debates about, well, where should we be spending our money? Even within the physics community, some people are nervous that if you put too much money into one pot, it's going to get taken away from another. And other people say, no, it's really just federal funding that's adding to our scientific effort. In any case, I believe that the demise of the superconducting supercollider was symbolic of a shift in U.S. priorities regarding particle physics compared to the rest of physics and the rest of science. I think from World War II until the superconducting supercollider, particle physics was kind of at the top of the heap. They were getting the big money, the big facilities, and there was a certain sense in which it was viewed as the most fundamental and therefore the most worthy of all the fields. And I think that idea has changed now. Particle physics is alive. very much alive, even though this big project disappeared. In future lectures, we're going to be talking about all the exciting stuff that's still going on in other accelerators and in other types of particle physics experiments. But I think now particle physics is one player among many, among all the branches of physics, and indeed among all the branches of science. Probably a healthy thing as well. I'd like to finish with the question of, what if we'd built this multi-billion-dollar machine and hadn't found the Higgs? I mean, this is a mathematician effectively telling you that we expect this particle of nature to exist. And it's quite compelling, but it's not proof. You've got to see it in the laboratory. This is science. And you could always imagine, in fact, you could easily imagine, that the Higgs wouldn't show up the way we'd expected. I think the argument at the time was, that would have been really interesting too. We have this extraordinarily successful model. And you could ask yourself, what would happen if you took the Higgs out of the model? And the answer is, well, some aspects of the model survive, but the standard model begins to collapse on itself. In particular, if you try to calculate what goes on at a couple of trillion electron volts of energy, then the theory would start to give infinities. In other words, the theory is fine still at low energies, but when you reach these superconducting supercollider kind of energies, or the European, believe their acronym is LHC, Large Hadron Collider, which is what they're building at CERN, because they're going to smash big hadrons, that's big, strongly interacting particles together. The theory would break down and give you crazy answers, which tells you that something is going on. It might be the Higgs. The Higgs is called a minimal theory. That is to say, it's the simplest possible mechanism we've been able to come up with, which is consistent with everything we know so far, and it makes the theory coherent. It's minimal. It doesn't mean it's true. And what I can almost guarantee you is that something has to happen at a trillion electron volts that we don't know about today. It's either the Higgs or something else. The symmetry of nature between electric and weak forces is going to merge or break down at those energies. We're not quite sure exactly how. We have a theory that makes a prediction, and we'd like to verify that. That's sort of the beauty of finding the Higgs. But if you find something else, well, that's great. Then we go back to the drawing boards and we reconstruct our standard model to fix it up in the Higgs sector. That would be the way we would express that. So the Higgs is the last piece of the standard model, the most important in the sense of understanding mass, fundamental property of everything, understanding symmetry breaking, which is sort of the key idea, the unification of weak and electromagnetic forces. And it's the one piece we've never really verified in the laboratory. We haven't seen one. We don't have any direct evidence yet. There was actually a hint at CERN just before they shut down for their upgrade. There were 1 or 2 events which were consistent but not sort of gold-plated. They were consistent with being Higgs. There was a big hoop-de-doop at that laboratory because the physicists said, gosh, let's keep running, and keep rolling those dice. If we've gotten 1 or 2, we ought to get some more. And now the laboratory director has this terrible decision to make. Do we continue running at this lower energy with a low probability, or do we shut down for 8 years, build the brand new machine, spend all this money, and then we'll be guaranteed to find the thing and learn all about it? And so it was an agonizing decision. And in the end, they decided to shut down, do the upgrade, and that's what they're doing. Meanwhile, we in the United States are continuing to look at Fermilab. So if they were correct, actually that evidence has since been essentially retracted. It looks like there may be other explanations for those events. So everybody, it would be great if we could find evidence for the Higgs already with our existing facility, but most likely we're going to have to go to a higher energy machine in order to do it. We really won't be able to say with confidence that the standard model is complete until we've either found the Higgs or found what else there is that plays the role of a Higgs. And at that point, I think we will be able to argue that the standard model is truly a complete theory of nature. So this is, as you can understand, a pretty big deal in the world of particle physics. It's one of the reasons why so much money and effort is being spent. And I can almost guarantee you that in the next few years, certainly in the next dozen years, you will be seeing newspaper articles about either the discovery, which would be spectacular, or the non-discovery, which would be equally spectacular, of the Higgs particle, either in the United States or at this new facility in Europe?